mysteries that it leaves unanswered are things like dark matter. So we know dark matter is another particle that exists in the universe, but we don't know what its properties are. We don't know what its mass is. We don't know what kind of charge it has, things of that sort. So what I largely do is that I come up with ways to detect dark matter. Okay, so if the dark matter had a certain property, I'll come up with a way to build a new experiment that will detect that kind of dark matter. Okay, does that make sense? So basically, if you thought the dark matter had property X, I work on building some instrument that will respond if the dark matter in the real universe has that property. Okay, if it does, then I would have detected dark matter. I would have identified what its properties are, and I'll be a very famous person. But I haven't done that yet, so I'm not so famous yet.
All right, thanks a lot, Surjeet. So I hope you understood what he broadly works on, right? So Surjeet, I think sort of the best way to take this forward is, given that a lot of them already have a lot of questions lingering on. So one way we could start this off with is by having a few questions that they have from the article that we shared with them, and use that to build whatever build on this session and for whatever time frame we are doing this. Does that work?
Sure. That could work, or I could also give maybe a 2-minute summary of dark matter if people don't remember it. I don't understand.
Okay, we could start with that. We could start with the summary and then start off with all the questions. Does that work with everyone? Perfect. Thanks a lot. We'll start.
Okay, good. All right. So if you look at the solar system, right? The solar system, the sun is the biggest source of mass, and then if you look at all the planets, Mercury will travel around the sun much more quickly than the Earth, which travels much more quickly than Jupiter, and so on and so forth. And we understand why that is, because you just do Newton's law, right? Newton's law tells you that the gravitational force goes as gm over r squared. And if you are further away, then the gravitational force is smaller and smaller, which means the velocity you can have as you go around needs to get smaller and smaller, right? That's the only way you can satisfy your standard equations of motion that you all know. So you would expect something similar should happen in the galaxy also. So if you look at the galaxy, the solar system is going around the center of the galaxy, right? As are many other stars. They're all going around the center of the galaxy. And you would again expect that as you go to the center of the galaxy, the star should be going around very, very quickly. And as you go further away, the star should start slowing down. Okay? That's again, it's a lot like the solar system. That's what you would expect. Now, what we see is that it's indeed true that as you go to the center of the galaxy, the stars do go around quicker and quicker. But what is happening is that as you go further away from the galaxy, instead of the velocities decreasing, they decrease for some time and then become constant. Okay? So this tells you that there is a lot more mass in the galaxy than what we can see with our eyes, what we can see with our instruments. Okay? So there should be some new source of matter out there which is gravitating. And it's only that gravity that can actually account for the fact that this star that is so far away is still able to go pretty fast around the center of the galaxy. Okay, and that is a new particle that we call the dark matter. And that is basically, we know it's a new particle, but we don't know anything else about it. We don't know its mass. We don't know what are the properties it has. And all we are trying to do is understand what it could be. So that's kind of a brief overview of the story of dark matter.
Right. So I hope you sort of have a rough idea of what dark matter is. So we'll now, Surjeet, what we'll do is we'll jump on to some questions which some of you have. So what we would do is whenever you have a question, just speak it slightly loudly. If he can't hear it, I'll repeat it so that the audio gets across to both sides. So we'll start off with the first question and try to turn in this so that you can see. Yeah. Sure. We have our, okay, all right. So we have our first question from our first student. Just repeat, mention your name and start with your question. Right.
Hi, sir. Sir, hi. I have the question that what are the properties of the dark matter that astronomers and scientists are able to find till date?
Good. So the only we know two properties about it. Okay, they both concern the mass of dark matter. Okay, so the only thing we know about dark matter is that it has to fit inside our galaxy. Okay. So now there comes a problem, which is that if the dark matter mass is very, very small, right? Then the by the way, have these guys done like de Broglie equation, things of that sort?
All of you have done de Broglie's equation, right? We just did it. It just did it. Yeah.
Okay, you just did it. So okay, now it's very useful then. So what does the de Broglie equation tell you? It tells you that if you have a particle, it is also like a wave, right? So if it is if the particles has some momentum, right, it has a certain size to it, right? Now if the dark matter is in the galaxy, we know its velocity because it is basically falling within the inside the galaxy. It basically has the same speed as the solar system. It's about 220 kilometers per second. Okay, that's the number that we know. Now, therefore, if the mass of dark matter becomes smaller, its momentum will become smaller and smaller, correct? Because P is equal to mv. And if P is equal to mv, then the de Broglie wavelength will go as 1 over mv, right? That's the formula for de Broglie wavelength, which means as the mass gets smaller and smaller, the dark matter's physical size, its de Broglie wavelength, will start getting bigger and bigger. Okay? Eventually, it will become so big that it can't even be inside the galaxy. Okay? So we therefore know that the mass cannot be that small. Okay? And that number corresponds to about 10 to the minus 22 electron volts. Okay, that's just a number which you get by taking the size of the galaxy and insisting that the de Broglie wavelength cannot be smaller than that. Okay, it has to be smaller than that so that it can fit in. Okay, that bound is true if the dark matter is a boson. Like, do you guys know what bosons and fermions?
How many of you have heard of bosons or fermions?
No.
Just a show of hands. Many of them are not aware of what bosons and fermions are.
Bosons and fermions are, okay. But you must have done this in chemistry, right? Like you did Pauli degeneracy principle.
We just did it 5 minutes back. Yeah. Pauli exclusion principle.
Pauli exclusion principle?
Yeah.
Okay.
Yeah.
The Pauli exclusion principle is true for particles like electrons, which have spin. They have spin a half. Okay. So they're called fermions. That's just a name for it. So Pauli exclusion principle tells you what? It tells you that you can't put more than one electron at the same orbital, right? If they have the same spin, I can only put one per orbital, right? That's the Pauli exclusion principle. So the same thing is also true for the dark matter. If the dark matter happened to be a spin half particle, then you cannot put more than one spin half particle in the same orbital, if you will, right? So think about the galaxy itself. So galaxy is like a potential. It has, the dark matter is confined to be in the galaxy. So once again, if you take the dark matter mass to be very small, then you have to have a lot of dark matter particles to make up for the same energy density. Does that make sense? We know there is so much mass in the dark matter. That is what we've observed experimentally. So if the dark matter mass becomes smaller, there has to be a large number to make up for the same total mass. But then if there's a large number, you run into problems with this sort of Pauli exclusion principle because you can't put more than one dark matter particle in the same state. Right? So much like how if you take your hydrogen atom and you try to put in a huge number of electrons, right? The size of the atom becomes bigger and bigger because you have to occupy higher and higher levels. So eventually the same thing is true for dark matter too, is that if you take it too light and if it happens to be a spin half particle like the electron, then eventually it will become to have the same number, the size of the thing will become very big. And once again, that won't fit in the galaxy either. Okay. So if it's a spin half particle, then the bound in the mass is about 100 electron volts. Okay, it has to be larger than that so that you can fit in. So those are two bounds we know about the mass of dark matter. There's another bound we know, which is that it can't be like super big. Okay, so if the dark matter mass is too big, there's something called gravitational lensing, and that is something that I think that you've heard about, but it's a very interesting phenomenon. It says the following: it's that if you have heard that gravity bends light. Have you heard that expression before?
Yes.
Yes? Okay. So gravity bends light, right? Now that gives you a new way to measure mass. So imagine you have like some dark mass here, okay? This is like dark matter that you cannot see with light. But imagine there is a star behind it, okay? And the star will be sending us light, right? But if there is this mass, the light will get bent as it comes towards me, like a lens. Does that make sense? So what people do is that they look at some distant star and they see how the light from that star gets bent as it comes towards us. And that now allows them to measure the amount of mass between us and the that distant star. Okay, so that is a way to measure how much mass there is, and that again tells us that the dark matter cannot be in like it sets a minimum, it sets a maximum size for how much the mass of the dark matter could be, and that is something about 10 to the 45 grams or something. It's a huge number. Okay, so anyway, there's a big wide range of possibilities for what the mass could be, but that's pretty much all we know so far. That it can't be too much light, it can't be very light, it can't be less than about 100 electron volts for a spin half particle, or 10 to the minus 22 electron volts for a spin zero particle, like a boson, and it can't be heavier than about 10 to the 24 grams. That's the exact number. So that's still a very large range where it's still possible.
How did you conclude that dark matter has to be inside the galaxy and not outside?
So the dark matter, the way we've observed dark matter is that we have seen how it affects stars, right? We basically know the stars are going faster and faster. That the distant stars are moving faster than you would expect. Okay, so if you have a distant star and it has to go around the center of the galaxy, gravity must come from the galaxy, right? It won't help you if the dark matter is very far away, because it has to actually help the star move around the center of the galaxy. That is basically how you know the dark matter has to be in the galaxy, because it has to move stars in the galaxy quickly enough.
Basically,
So the range of stars after which all the stars have the same velocity, that ranges from like half of the radius or more than that?
It is like I would say it's pretty much half and so on and so forth. Like I would say about half the galaxy. Yes.
Rushikesh here has one more doubt.
Okay.
Yeah.
Hi.
You can-
How this matter is bound together? If it remain unaffected by electromagnetic force, do it has strong nuclear force as internal force or another force?
So we don't know what else it has. Okay. So that is part of the question. So we know it does not have electromagnetic force. We know that it does not interact with us with a strong interaction. That is something we know because we've looked for it. But other than that, we don't know. So in fact, one of the hypotheses out there is that the dark matter could interact with us with a weak nuclear force. That's a possibility. Okay, and people are actually going out there building experiments to test that.
If this force is a single force, do this force will be a unified force of all four forces that we have, or this has existed at the start of universe when universe?
So it is unlikely that this will be a unified force yet. So of course, it is possible that if it is more like if the dark matter is interacting with us with the weak nuclear force, then it is not a unified force. Okay, but it is possible theoretically that the dark matter, if it doesn't interact with us at all, then in fact it could interact with us with this unified force, but that would be very, very hard to see. It would be very hard to detect.
Does that answer your question? Roughly answer your question. Yeah. A lot of this is, in fact, even new for me. So even I'm learning a lot from your conversation. Moving on to further questions we have. So we have a question from Umesh. Umesh, just say it loudly because you're sitting slightly further away. Yeah.
Hi, my name is Umesh. My question is, how did scientists found the percentage of dark matter in the universe?
Good. So that's a good question. So basically, what we do is the following, right? Is that we know how fast these stars are going around the center of the galaxy. That's a measurement you can do, right? By looking at a telescope, you can say, oh, that guy is going so fast. And then what you then do is that you look at the galaxy and you count the number of stars that are actually there, basically, right? You get a rough idea of how much mass there actually is in gas and stars and things of that sort. And once you have an estimate of that, you can then ask, how much more do I need? How much more mass do I need in order to fit the data? Okay, and that is basically how we come up with the number that there needs to be 5 times as much mass out there than what we can see. That's basically how it's estimated.
Got it? Yeah. I think we have further queries. We'll go one by one. We'll go with your name and just speak your question. Yeah.
Hi, sir. My name is Ankit. My question is that how dark matter is created, and if there is any way to destroy the dark matter?
Good. So we don't know how dark matter is created, because that's actually one of the other puzzles that we try to answer. because we don't know, like, no idea what its properties are, right? We don't know its mass, we don't know anything else. So one of the motivations would be that if we discover dark matter, if we figure out what it is, what properties it actually has, then it will give us some understanding into how the dark matter could have been created. Okay, so until we answer that question, we won't know how it was created, and we also won't know if it can annihilate itself, if it can destroy itself. So there are certainly particles like electrons. For an electron, there's a particle called the positron, which is antimatter, right? And the two of them can get together and annihilate and become photons. That's a possibility. But there are other particles like a photon, like the photon is its own antiparticle. It doesn't really annihilate itself, right? They're more or less the same particle. So we don't even know those kinds of very elementary properties about the dark matter. We don't know if it has its own antiparticle or if it can annihilate itself. We don't know that yet.
Right. Then we had questions. Yeah, we had another question from Sameer. Yeah.
Okay.
So we know that the dark matter could easily pass through the common matter, but does it has the capacity to pass through a black hole which is so dense?
So that is one thing that we know about gravity, is that if something goes into a black hole, it gets trapped forever, right? Because we know that the one thing we know about dark matter is that it experiences gravity. That's how we've seen it, right? We've seen that dark matter exerts gravitational forces on other particles. And the black hole is something where gravity is so strong that nothing can escape it. So the dark matter goes into a black hole, it gets trapped.
Right. Yes, we have one more question. Okay.
Sir, do the thing that we call space is not space, but it is the dark matter that do not interact with other matters and can pass easily through it?
Well, so space is basically something that exists without particles being there, right? So space is just like, in a sense, you think of it as an empty stage, and particles are like little actors walking on them, and there are like different kinds of actors walking on the stage. Some of them are actors that you like, that will be people like standard matter, like you and I, and then there are other actors out there that would be like dark matter that we don't know who they are. But space itself is just an empty thing. Certainly, it's quite independent of the existence of particles on it.
Right. Anybody? Further questions?
Praneeth has a question.
So does dark matter affect our life in any way?
No, because if it had, we would have seen it, right? So, like, one of the big difficulties of dark matter research is that it's very hard to find it, right? So we have to work extremely hard to detect dark matter. It's a very because that's why we don't know like any of its properties yet, other than these very elementary things like some bound on its mass. We just don't know anything else about it really, and that is mostly because it's very hard for dark matter to actually interact with us. So that's why it doesn't affect our life. I mean, it doesn't affect our life today, but there is a very global sense in which dark matter has affected the whole universe. Okay, basically because if you ask how do galaxies form, because if galaxies did not form, we would not exist, right? So dark matter is very important for the formation of galaxies, because dark matter provides most of the mass in the galaxy, right? So the dark matter did not exist with the kind of properties that we know it has, then the galaxies would not have formed the way they have. So in a very meta sense, it does affect our life, because if there was too much dark matter, it's possible that the galaxy would have become entirely what is called dark matter dominated, in which case it wouldn't really have too many stars. And if there were no stars, we wouldn't exist, right? But it doesn't affect our day-to-day life.
We have a question there.
Sir, I'm Anand. I just wanted to ask that dark matter is at a constant place or it is moving?
It's moving. It is much like how the solar system. If you look at the center of the galaxy, the solar system is moving around it, right? Like the Earth is moving around the sun. The solar system itself, the sun itself, is moving around the center of the galaxy. So similarly, the dark matter itself is moving around the center of the galaxy.
All right. You have more questions? So I have a question here, since
Okay.
me as well.
Yes.
So to me, what I want to understand is So for most of this dark matter, like for instance, we study that a lot of the reason we study matter is there is some possibility of conversion to energy or some application in that way. Is there some motivation behind studying dark matter which sort of might help us in the future apart from just knowing more about atoms and matter?
Well, I mean, for a physicist like me, no. I mean, for me, I just care about the fact that this thing exists, and I want I want to understand what it does, right? So that is what drives me, and I think most of my colleagues. But it's indeed the case that depending upon the answer to what dark matter is, then it's all sorts of new possibilities may arise. So there are certainly some kinds of dark matter which are, I would say, pretty useless in the sense that they won't do anything for human life. But there are other sort of dark matter particles, other possibilities where it can be very dramatic. So it all depends upon the answer. So like one dark matter candidate that still exists today is that the dark matter could be like tiny little black holes. Okay. So if that happened to be correct, then of course you would have your own personal little black hole to play with. And that can then do all kinds of amazing things if that happened to be true. Like, for example, one of the things that we talk about would be that if you had a black hole, it's a great way to swallow garbage, right? You just put a little black hole, the black hole will just eat up all of your garbage and it just disappears. So, of course, I mean, I don't know if the world, if that is the answer, but if that happened to be the answer, then the world would be very cool.
So, dark matter interact with each other. These dark matters.
Ah, very good. So, what we know so far is that dark matter has not interacted with itself. Okay, so basically, there is one observation we have had, which is actually a pretty grand observation. It is the fact that there is this one. Much like how the galaxy is a lot of stars, there is also something called a cluster. Okay, a cluster is basically a whole bunch of galaxies going around each other. Okay. So what we have seen is we have seen two clusters that have actually gone through each other. Okay, and as the two clusters have gone through each other, we've observed that the dark matter has not gotten hit. Okay, and the way we've observed that is basically it sort of uses this gravitational lensing, the thing I just talked about earlier, which is that if you have two clusters, right, the clusters are going through each other, you would expect all of the gas in the cluster to get hit, and they get stuck like somewhere in the middle. But the dark matter should just go through, and the dark matter has in fact gone through. And the way we know that is that we've basically observed this gravitational lensing. We have tried to sort of taken a picture of this cluster as the two things have gone through, and we have seen what's called a map of the lensing. So we kind of look at some star behind, and then we say, oh, this light from the star is coming towards us, but it gets bent over here. So this is where all the mass should be, okay? But the gas is somewhere in the center. Okay, so that's basically how we know that the dark matter really exists, because like we see that all of the stuff we can see, all the stars, the gas, that's all over here, but all the gravity is somewhere else. Okay, so that's basically how we know it's a particle. But it also tells you that as the dark matter, as it goes through, it hasn't hit itself. Okay, so of course it could hit itself at a slightly weaker rate. That we don't know yet, and that is something that actually we are pursuing as a research project to try to understand those properties. So that's all we know so far, that it hasn't, in that one cluster that it went through, it hasn't had a chance to hit itself. So there is some upper bound, if you will, for what the interaction can be, but obviously it can interact below that.
Right. We'll first take a question, one more question from here. Yes.
Myself, Saurabh, and I want to ask, what will happen if there is no dark matter?
What will happen if there's no dark matter?
Yeah.
Well, first of all, the galaxy would not be quite what it is. So we would lose about a factor of 5 the amount of dark matter, in the amount of mass that we actually have in the galaxy. And this may not seem like a very big deal, but it is kind of a big deal in the following way. So if you ask, how do galaxies form, right? How do we, why are we, existing in galaxies and things of that sort? That's something that we've actually understood in the last decade or so, okay? And the way it works is the following. Have you guys heard of something called the cosmic microwave background? No. So, okay, this is an interesting thing. So, you've heard of the Big Bang Theory?
Yes.
Have you? Okay. So, why do we believe in the Big Bang Theory, okay? the strongest experimental evidence for the Big Bang is that if you take a radio, okay, and stick it out in the middle of space, in the middle of empty space, then it turns out that no matter which direction you stick it in, you end up getting a signal. Okay, and this signal is really coming from the fact that when the Big Bang happened, right, there was a lot of energy that was actually released, and that is essentially there all over the universe, and it's slowly cooling. Okay, so essentially the fact that the Big Bang occurred is something we can test today by taking a radio and sticking it out in the middle of the night, and finding out that no matter which direction you point in, there is some photon signal coming there. Okay, that's basically how we know it so well. And so that is something that we have understood extremely well. And that raises an interesting question, which is to say that if this radio signal is the same everywhere, it's sort of representing some kind of heat background, okay, some kind of a bunch of photons going around. So if that quantity is the same everywhere, how is it that we ever produce galaxies? Okay? And what we know is that while that temperature is uniform throughout, it basically has a small variations in temperature from one place to another. Okay, so in this part of the universe, in this direction, the temperature is slightly colder than this other direction. Okay, and what that means is the following: is that the hotter spots will have more gravity than the colder spot, which means they will drag more matter inside them. Okay? So the moment you have a little hot spot and a little cold spot, over time the hot spots become hotter and hotter because they drag more and more mass, while the cold spots become colder and colder because they keep losing mass. Okay, and that is basically how galaxies form, because they're able to drag all this matter from all the cold spots into the hot spots, and the hot spots become bigger and bigger. So it turns out that dark matter is very important in that story, because dark matter is actually able to, because of that factor of 5, it turns out to be an important number, just for a numerical reason. It actually allows for the existence of big galaxies, because that factor of 5 somehow manages to pull in enough matter quickly enough that these big galaxies can grow. So if we didn't have as much dark matter, the galaxies would basically be about 1 million times, it turns out, less big. Okay, so you have like 1 million times fewer stars and things of that sort.
All right. We in fact have a couple of people who have joined from their home as well. We're just figuring out how to relay doubts from them. Meanwhile,
Sure.
there was, are there any further doubts? We had one there. Yeah. Good.
So you told that two clusters collided and dark matter didn't react. Then it can be probability that they repel each other.
They did what? What's the final thing you said?
And they can repel each other.
But see, if they repel each other, once again, right, we know that, so the point is, if they repel each other, they will of course go the opposite way, but in fact not always the same rate, because if two things are colliding and they're sort of repelling, they'll actually go in all kinds of directions. So what we've seen is that the dark matter has sort of gone through, and the whole lump has basically gone this way, right? So normally if you take a bunch of particles and you throw them at each other and they're repelling, right, they'll get scattered in all kinds of directions. There is no reason for them to just go as a whole into like one particular thing. For example, take two rocks, okay? If you bring the rocks towards each other, the rocks are actually repelling, right? That's what happens when you take two rocks and you throw them at each other. They actually smack and go away. But then you take them and you smack them, they'll actually break and go in all kinds of random directions, right? They won't kind of go together as a one whole lump through the other. So that's basically how we know that.
They're neutral to each other's gravity.
Pardon me?
They're neutral to each other's gravity.
Gravity, of course, is something that is a very weak force, right? So, of course, that's a strange thing saying that, because we are usually dominated by gravity. But like gravity, I mean, that's one of the other big puzzles of physics. Okay, think about how easy it is for you to lift an object off the ground. Right? I can do it super easily, right? Without even thinking. And if you think about it, I can lift this object even though the entire Earth's gravity is pulling down on it. Okay, so the electrical forces in my fingers, my finger is really small compared to the Earth, right? But the electrical fingers in my hand are so strong that they can easily overwhelm gravity, right? Despite the gravity of the entire Earth sort of pulling down on this thing. And and that's a big puzzle. We don't quite understand why that is. But for that same reason, gravity is a very weak force. It's unable to really distort this too much. So even though they're attracted by their gravity, they're unable to like really get destroyed all that much.
Yes.
So can we explain the evidence of dark matter in terms of mathematics? In
terms of mathematics, you mean in terms of like, do you mean like changing the law of gravity, or what do you mean by mathematics?
Mathematics means some laws of Newton.
Good. Yeah, so that is exactly what this cluster example shows is not possible. So until this was observed, there was actually a theory like what you were trying to do, which is that people did try what is called MOND, or modified Newtonian dynamics, which was supposed to be a way in which you would modify Newton's law and say, oh, it's only a factor of 5, right? So why can I not do that by just changing the law of gravity? But that is exactly what this cluster example proves is not possible, right? Which is that if you had this cluster, the dark matter is here, the gas is here, and we know that all the, like from the lensing, we know that all the gravitating mass is sitting here. Okay? So that way, if you're modifying your Newton's law, you would expect that whatever it is that you're doing, the gravity would still be concentrated towards the gas itself, and not where the dark matter is, right? But that is contrary to observation. So your possibility was, it was certainly considered as a serious theory, and people were thinking about it for, I think, over like 20 years. But then until we went ahead and actually made these measurements, now we know the answer. That's not quite possible.
Right. So
yes, we have one more doubt here.
It is believed that during Big Bang, all the planets will collide and destroy each other. Will the dark matter also do the same?
Say that again. I couldn't hear you quite well.
Say that loudly. Yeah.
So during Big Bang, it is believed that the planets and stars will collide. Do the same for the dark matter.
So he's asking. So just to rephrase what he said. So he's asking. Yeah. In the origin of Big Bang, it was believed that everything collided and formed. Right? Are the origins of dark matter similar?
So that's not how the Big Bang we think. Well, nobody really knows how the Big Bang actually works, right? So the Big Bang we just think was a magic moment back in the very early universe, where boom, everything came into existence. We have no idea what happened or how it came about. What we do believe is that, like, that it produced a lot of particles, okay? And yeah, we do believe that along with the standard model particles that that we know exist, the particles like electrons and protons, things of that sort, the dark matter was also similarly created. It must have been because it exists, okay? But until we know more about its properties, we can't really figure out how it came into existence.
I'm really figuring it out. Do we have any more? I saw some raised hands somewhere. So I have a question. I have one more question as I was listening to this.
Okay.
So whenever you say dark matter, the first thing that comes into mind is this is something which is extraterrestrial, which is not in Earth. Is there any evidence of dark matter being there on Earth?
Yeah. So in a sense, like, so in a sense, we've never actually observed it, right? But the point is, it's existing all over the galaxy. So it'd be very hard for it not to, in a sense, be in the, going through the Earth. Basically, because once you look at the, the whole galaxy has dark matter everywhere. Okay, so think of it as some kind of a wind that exists everywhere in the galaxy, right? And we're just a little boat or whatever moving through that wind. So you would require some very powerful reason why somehow the dark matter wouldn't get to us, because it's like, I would require. If you're going through wind and you don't want the wind to hit you, you must build some shield that blocks the wind, right? But the dark matter has very weak properties; it's able to get through pretty much any shield. So how will you even block it? So that's one of the reasons why it would be exceedingly unlikely, if not really impossible, for dark matter not to go through us.
Do we have any further questions? We seem to have one there. You have a question there? Sorry?
You can ask.
You can ask the question. Yeah. Yeah.
So,
yes.
So till now, dark matter has never made an eclipse.
Eclipse. Well, the dark matter is not a particle that interacts with light. That is something that we know, right? So, in fact, if it could eclipse things, then we would know that it actually that it's not dark matter in a sense. That it's basically interacting with light, right? So that's why we call it dark, is because it's not interacting with light. So that is the reason why it could have never done an eclipse, basically because as light goes through the dark matter, it doesn't care. It sort of goes right through it.
Then why
There's no shadow or whatever that it creates.
Right. So we have one more question building onto that here. Yeah.
So why consider it matter then? We can consider it energy.
Good. So, so when we say it's matter, right, what we really mean is that it has a non-zero mass. That's all. Okay. So photons, which that would be light, right? That would be radiation. Photons have zero mass, but they still have non-zero energy. That is something that you guys will learn in your as you do some quantum mechanics or whatever. But dark matter, we know, definitely has a mass, right? Basically because we know that it's a part of the galaxy, and as part of the galaxy, it needs to have a mass because gravity cannot bind it otherwise. So if you think about it, it's only a black hole that is able to capture light, right? So we know the escape velocity of the galaxy. The escape velocity of the galaxy is about like 500 kilometers per second. So if the dark matter, and we know the dark matter is in the galaxy, which means it is moving slower than 500 kilometers per second, okay? And that basically means it is not traveling at the speed of light. And as you go and learn more physics, you will realize that basically the only particle that can travel at the speed of light is light. It has to have zero mass. And any particle that has a non-zero mass necessarily travels slower. So the fact that the galaxy, so the fact that the dark matter is in the galaxy and it is moving slower than 500 kilometers per second tells us that the dark matter has to have a mass. That's why it can't just be like a photon or whatever. It can't just be a massless particle.
All right.
So,
we hear a question from, where is this? This is from
Akhil.
Akhil.
Okay.
Hello. So we
yeah,
have.
sir. Sir, I joined late, so I would like if you would tell me what is dark matter in short.
Well, so basically what dark matter is that we have looked at take the solar system, right? The solar system is a place where there's a sun and there are planets that are going around it. And as you go further from the center of the solar system, you notice that the velocities, the speeds of planets slow down. Okay, Mercury goes much faster than Pluto, for example, and that is basically because the if you think about the whole process through like Newton's theory of gravity, there is gm over r squared. That is the force that is making things go around. While as you go further away, the mass remains the same. It's still the sun's mass, while the distance keeps dropping. Right. So the available force decreases, which means the amount of centrifugal acceleration that you can get is smaller and smaller, which means that the speed has to go down. Okay. So that makes sense as far as the solar system is concerned, and this is what we've observed. But now, if you look at the galaxy itself, what you find is that it is indeed the case that all these stars are going around the galaxy, right? So what you might indeed expect is that as you go further from the center of the galaxy, you might expect that all of these stars should go slower and slower, much like the solar system. But what we find is that indeed it starts becoming smaller as you start going a little bit away from the center. But after a while, the speeds become constant. Okay, so instead of dropping down, and that is weird because well, that tells you there should be more gravity there than what we can see. Right? You can't just be there can't just be one single object that's doing all the gravity. There needs to be more mass out there, and that is exactly why we think there's dark matter.
Akhil, so just in case you want to check, so we had a 30-minute discussion. We'll share the link of whatever we discussed. You can view that later in case you want to go through what we discussed. All right?
Yeah, sure, sir.
Yeah. So Surjeet, I think it's sort of it would be a good time to sort of wind up here. So what we would like to wind up, since there is sort of we have mostly people believe that they have got a rough idea of what they expected from this. So it would be good if you could sort of share some of your lessons, given the fact that many of them are from the 11th grade where they're just starting to learn physics. This is the first time they are being accustomed to challenging physics and chemistry concepts. It would be a good idea for you to share in general what exactly are the things in case they want to sort of move towards learning more in this area. What are the things that they're studying right now which might be relevant for them, which would help them understand this better?
So, I mean, it turns out this is pretty simple. So, it's basically Newton's gravity. That is something that you need to know, right? Obviously, this is where a lot of the measurements come from. So, you want to be able to maybe understand things like how light actually bends, right? That's something that you might want to know better, how that actually happens. You probably also want to learn a little bit about like things like quantum mechanics.
Yes.
I've forgotten what I knew in 11th standard. I guess people don't learn that kind of stuff. Okay, so that would help you a little bit about that kind of thing. Most importantly, I think is like, I mean, I don't know if there's anything that you will learn in school immediately, but I would say keep in touch with stuff like science news, right? So you probably want to understand something about the cosmic microwave background, right? This is what we mentioned. This is basically how we said that the how galaxies actually form, right? The fact that if you stick a radio set anywhere out in the middle of nowhere, you still get a signal and something is happening. So you might want to learn about stuff like that. So I think that would be my advice. Learn something about gravity, and then learn more about the cosmic microwave background. I think that would be a good way to start to appreciate these questions.
Because I think honestly why I asked this question is for a lot of us this seems like something which is very complicated, but just as you put, the basics for that are very simple. So it would be useful for them to listen that it's not really as complicated as it seems to be.
Oh, it's certainly not complicated at all. I mean, the thing about science, look, just like you guys, when I was in 11th standard, I was also interested in questions, right? And like bingo, 15 years later, I'm a physicist, right? So it's not like one day I was born and then I immediately knew all these answers. Of course not, right? The point is that there's a path towards answering these questions, and it's just your curiosity. Like the more you're interested in these kinds of questions, you have the internet. You can just go and figure out answers from there. I'm sure I'll be happy to talk to you guys again about these matters if you're so interested.
All right. Thanks a lot, Surjeet, for that. That was definitely very inspiring for a lot of our kids. We hope to get in touch again with you. I'm sure they're going to study more and bombard with you more questions in the future. Thanks a lot for making time again. We hope to see you again. And with that, we sort of wrap up this session.
Sounds good. Okay, it was fun. Take care.
Thanks a lot, Surjeet.
Sure. See you.
Okay.
Bye.
Stop.